So how's everyone been liking the class so far? Favorite class? All right.
One's taught at the beginning of this semester.
Yeah.
There you go. No, the one-liner ones were very interesting. The ones that were recorded for the last couple of classes.
Oh, was that Andrew Farrington who did that?
Yes.
Yeah,
Yeah,
he's pretty good.
yes.
Let's see, I forgot to share my other screen. All right, so there's you guys. All right, there we go. All right, so I guess with the Aspen stuff, did you guys have an Aspen model or an Aspen license to work with, or was it mostly just him kind of working through it with you guys?
We had one.
Yeah, I don't know. Cool. Okay. Yeah, we use Aspen quite a bit in the real world. But I guess we're shifting focus today. We're moving on to distribution protection. So just as a recap, I've got here kind of a little bit of a sample grid, just to kind of give a recap, but then just kind of pinpoint where we're going to be focusing our time. So as we discussed before, you've got your generation, right? That's where the power is converted from some sort of energy to electrical, whether it be mechanical, photovoltaic, whatever. Usually that gets stepped up onto the transmission system, which I usually think it was 115 and above, but it's like this one has a little bit of a higher criteria. Drops it down to subtransmission, sometimes called transbution. Sometimes it doesn't do that. Sometimes it goes straight from transmission to distribution. It really depends. And these are terms, but it really has more to do with how far we need to transmit that power. If we got to transmit it 100 miles, right, we're going to have a high voltage to reduce the losses. If we only have to go maybe a mile, right, it's a short run from that distribution station to the loads, and maybe we got something lower like 4 kV. But from there, right, we go down to primary distribution. Yeah, that's the voltage range we'll be talking about today, kind of that 4 kV to 35 kV. Right, that's kind of what you guys are probably used to seeing on your overhead distribution lines, following roads. What we're seeing here. And then from there, usually you're going to have those small distribution transformers on the top of the poles, right? They bring it down to that 240, 120, power that comes into your house. But yeah, really, if you need a visual, that's kind of that voltage range we're going to be focusing our time on today. Maybe one more thing. I've actually also found in the protection world, you would think, this higher voltage equipment would be more difficult to protect. That's actually not always the case. You'll also find this high voltage transmission, they're willing to spend a lot more money on it. So a lot of times the protection schemes are, if anything, a little bit easier because you get the best of the best. Whereas you get down here, they don't have that funding. And sometimes engineering creativity makes up for expensive equipment. So yeah, there's actually some interesting protection schemes that you run into. So characteristics of a distribution system. We talked about the typical voltage ranges. There's different types of systems. A 4-wire solidly grounded systems are most common. By 4-wire, I mean A, B, C, into ground that gets run out. That ground allows for 2 voltages. You can check your phase-to-phase voltages to get that ground point. You can get a line to ground voltage. Grounding makes it safer for technicians. Right, if there is any incidentally energized equipment, right, it's grounded, or it's ground short, it trips something off, takes it off the system before maybe someone else comes in contact with that and they become the ground point. So it's safer, and it allows for ground fault over current protection, which is a little bit easier to detect faults with than ground over voltage protection, which would be what you need in an ungrounded line. So there are 3-wire delta systems. They're less common, but they exist. Very uncommon in the state of Maine, I'd say. We do a good amount of work in the state of New York. I've seen a lot of them in New York. I've seen more of them in New York than anywhere. One thing about a 3-wire delta system is it can technically stay in service with a standing ground fault. What ends up happening is that faulted phase goes to 0 volts. The unfaulted phases maintain the same phase-to-phase ratio. They do experience an overvoltage, which could be damaging to equipment, but all of the load will technically still run. It wouldn't be until that second fault occurs, until an overcurrent element would take it off. Distribution systems have been traditionally radial. As we talked about last time, that meaning there's only one source. Current's only going to flow in one direction. And then, man, every year I do this class. When I say distributed generation is becoming more common, yeah, I assume all distribution lines have some sort of distributed generation on them now. It's everywhere. You see it driving down the road. It's not becoming more common. It's just everywhere. So, let's see. I wonder. Sorry, I'm looking for an option here. You guys can't see it with my other screen. I can't do anything with. Okay, there we go. Typical configuration of a distribution feeder. A feeder, I guess the definition is one of the circuits out of the substation. It could be fed from a breaker or recloser at the substation. I guess another term, the main feeder is the backbone of the circuit. We'll have an upcoming slide where we can see, more visually, I guess why that term makes sense. Then you got branches off the main feeder. They could be called laterals or taps. Now the main feeder is usually that 3-phase, run. Taps can be 1 phase, they can be 2 phases, or they can be 3 phases. You could have a 3-phase industrial load coming off that distribution line. That's common. You could have a 1-phase to ground, tap going off, or you could have a 2-phase line to line going out. There's all sorts of different combinations. I would say 1-phase loading should be attempted to be evenly distributed. What can end up happening there is if you were to put all of that loading on 1 phase, right? All that phase current was, let's say, on phase A. You end up with an imbalance, and that imbalance creates a ground current, and that ground current is sensitive, usually more sensitive than the phase, so you might have a false trip. It's it's happened definitely before, but you try to prevent it by calculating out your load and evenly distributing that across the 3 phases. And then taps generally have their own protection, either fuses or reclosers, which, like I said, we're about to see an image that'll see why. So this is kind of a visual of that distribution circuit that we talked about. This situation has a breaker at the substation. And that little square is a pretty typical breaker symbol. So this 3-phase portion right here, that's what I was referring to as the backbone, right? Kind of see it as a spine looking thing. Right, that's the backbone of that distribution feeder. And each one of these is the laterals or taps that we talked about. And you can see some of them here are 3-wire, 4-wire, 2-wire. It's a good job of splitting those all out. And then you can see, a lot of these have fuses. Looks like we have a recloser right there that kind of splits the backbone. We've got some switches. Looks like we've got a cat bank, transformers, all sorts of stuff here. Let me see. Can I get a pen? There we go.
So does that arrow on the left mean, the distribution line goes underground? That's all that triangle means?
Yeah. I don't have like a legend, but that appears to be what it's saying.
Okay.
Yeah. And different people show that different ways. Sometimes people have, they'll change it to a dotted line. But I'm assuming that's what that means, Shane.
Mhm.
So
Awesome.
Yep. So the reason they've got so many different protective devices on here, has to do with that relay coordination that I think I brought up in my last class. I'm sure Andrew brought up in his Aspen class. So, this breaker right here, right, that's going to have some overcurrent elements, right? It's going to have some 51 elements. And then these fuses, right, those, the more current you have, the faster that they blow. So these are all for coordination, right? The goal is if a fault happens right here, current's going to flow through here. We want that fuse to be faster than the overcurrents on our breaker. So that way just the fuse can, pop. These guys unfortunately lose power, but they had to, right? They were on a faulted phase. And then hopefully if you live over here in one of these houses, you didn't lose power. Right? That's the goal. Same with this recloser that they put in down here. It looks like the whole goal was to kind of break that backbone in two, right? Same thing, fault happens here. Make this guy faster than that guy. These guys, unfortunately, have to come offline because their backbone was faulted. But hopefully everyone over here still happy with power, doing things that people with power like to do. So, I guess I thought that was a good visual.
Could I ask, back on that first? It looks like the transformers on the top right, one of them has a arrow coming off of it, the other doesn't. What does that mean?
Okay. I don't think it means anything. I think it just in this situation is a drawing inconsistency. I honestly think it just means that this one they had room for one, and that one they had text in the way, so they just didn't draw one.
Is it 120, 240? I know like on a small distribution transformer that the way you get 120 versus 240 volts is just tapping it in the middle versus all the way
Yep.
to one side. Is that why? I just see right under it, that 120/240.
Yep.
Maybe.
Yep.
Maybe that's what, I don't know.
Yep, that's exactly right, Shane. So yeah, on a transformer like this, what would happen is you'd have your medium voltage line, right? Let's say it's a 34 kV system, which means you got about 19.2 kV to ground, right, on a single phase. So that transformer is going to have one winding on the primary. It's to ground. So what ends up happening on the secondary is it is still single phase, right? This is what we all have in our houses, by the way. It is single phase. It is 240 volt single phase, but you're exactly right. They have this center tap, which is grounded on the secondary side. So on your house, your wall outlets will be 120. But then if you want to plug your stove into 240, you can. So, yep, that's what the 120, 240 means. And again, that's how all of our houses are, unless you got something special going on. But for the most part, that's how the houses are going to be. So, yeah, great question. I really appreciate questions.
Sure.
So, yeah.
So for
oops.
places that have a 408 volt, do they have to do a special transformer?
So a 408 is actually usually going to be a three-phase transformer. And there's a bunch of different types of transformer configurations. But yeah, 408 would usually be a different type of transformer. It'd usually be a three-phase transformer. And what they'll usually have with that three-phase transformer is maybe it'll be a Y, maybe it'll be a delta. Sometimes it'll be, a delta with a high leg. There's all sorts of different ones. But it all has to do with that ground point and, where you want to grab your voltage from. So like on a 480 system, what you would normally see is, it was a three-phase transformer. Let's say it was a Y in the situation. Bump those out a little bit. Similar to what you have here, right? You have that ground point. You could do 120, 120, or 240. You might see something where you have 480 phase to phase, or you could go 277 phase to ground. And then right there are different combinations. This one's a little weird where you can go, this is that center tap there. You could technically go get a voltage, from this value. You could get a voltage from that value. That gives you one more option. Like I said, there's a handful of different transformer configurations. But yeah, at your house, this is definitely the most common one. Maybe in an industrial facility, that's more what you're used, you might see. Yeah, I love the questions. I'm not just saying that. I really do. It's good to have it be interactive. So getting back into the radial feeders. So they're the simplest, lowest cost, and most common type of feeder, radial. I guess that might be wrong now, right? The amount of distributed generation technically would make them not radial. So that, that may not be true anymore. So current magnitude is greatest in the main feeder at the substation and less out towards the end of the feeder as current leaves the taps. Yeah, that makes sense, right? You got 100 amps right here, right? You got, 10 leave here, 10 leave here. Okay, now we're down to 80. Right, that makes sense. We're gonna have the most current, closest to the breaker. As current lessens, the conductor size may be reduced. Yep, that's true. Those spots that have higher current need bigger conductors to dissipate that heat. But you also got to think about voltage drop, or you're going to drop more voltage on a smaller conductor. Maybe a situation where it may be able to handle less current, but it drops too much voltage, and you guys aren't going to get that 120 that you need or 110 that you need at your house. You guys may drop below an acceptable range if they don't size the conductors correctly. And then also that theory kind of diminishes. One thing that they will do, you see this here, this normally open tie. Sometimes they'll take, if we could think of a carbon copy of this feeder here, they'll tie it in right here, right? They'll have all the radials attached and everything. And what they'll actually do, say, okay, we got to take this breaker out of service. We got to do maintenance. We got to do this, that. We're going to take it out of service. We're going to close this tie. And then we're going to feed everything from this, from this circuit. And it's really going to see double the load. In that case, when I was saying, okay, this conductor could be a little bit smaller, well, not anymore, because now it's got to carry all this stuff. So maybe that's a situation where, that's not necessarily true. But in general, just trying to say, more current here, bigger conductors here, less current here, smaller conductors here. So. And then, note that this was a radial feeder. Yeah. Looped feeder. A looped feeder is one that goes through the load area and then returns back to the bus. We'll have a visual for that also. Provides two separate paths for the current, which we'll see that. A lot of the times they'll have a loop tie switch or breaker that may operate as normally open or normally closed. That is exactly what we talked about here. So loop feeders would typically be used in high priority situations. And a lot of the times in those situations, you will see it be fed from two separate buses or transformers, depending on how of a high priority that is. Can someone think of maybe a high priority situation where you would want to feed load from two completely separate places?
Hospitals.
Bingo. Yeah, good call. Yep, that was actually going to be my example. A couple of years back, I did a project at Togus, which is a veterans hospital here in the state of Maine. And that's exactly what they had there. If you could think, they had Togus, which was the hospital. What they actually had was from one part of the grid, they had a feeder come in and they could feed Togus from it. On the other side, a completely different side of town, really, they could feed Togus, from that also. And there was a bunch of switching here in the middle to make that all work, as well as I think they had close to 10 backup generators. Hospitals don't mess around. But the whole goal here was, this whole bus could go down. The transmission system that feeds this bus could go down, right? You could have catastrophic failure over here. Well, that's all right because we are good to go over here. So, yep, hospital was definitely a good example of that. You can see in here in this situation, this is not the case, right? This is fed from one breaker where things go around. You could also have it maybe fed from two breakers if you wanted to, or like I said with that Togus example, fed from completely different substations. But yeah, this is a situation. They got that loop tie disconnect. The great thing about this is they could really isolate. They have a ring, right? They can really isolate any part of this if they need to, and keep the rest of it in service. So, like, let's say they need to do repairs on this portion of cable. Or I guess they don't have switches right there. It really have to be right this portion of cable. Right, open that switch, open that switch. They can do that, and everything else can still be energized because it goes around that loop. So yeah, I guess a common arrangement there. So I know we talked through some of the common equipment here. So we'll get a little deeper into that. So switches, a device for making, breaking, or changing the connection in electric current. Usually switches are not meant to interrupt, fault current. You can have load break switches, or you can have non-load break switches. But yeah, I guess they're exactly what we're describing, right? They're just basic switches. The symbol for that, we can see them right here. Right, that's a typical symbol for a switch. If it's a load break switch, that's awesome. You can, interrupt load with it if you need to open it. If it's a non-load break switch, you actually need to isolate it first before you can open it. Right, it has to have no current before you open that guy. So a fuse, it is your most basic overcurrent protective device. Right, it's got that that fused portion in the middle there. Right, the more current that goes through it, it gets hot, it melts, it opens when it melts, and it's successfully isolated any current. It's good for overloads or short circuits, right? Anything that'll make it hot. Great thing about fuses is they typically don't fail. Right? That's you're never going to have one of those not melt. As opposed to maybe some of these other devices where they have mechanical operations that got a little bit more going on. So you got your reclosers. That is a more I guess complex protective device that trips and recloses a preset number of times to clear transient faults or to isolate permanent faults. So you'll see those at the top of poles a lot of the times. You'll probably notice them more often once you know what they are. but they can interrupt fault currents usually. You know, they've got some reclosing characteristics that we'll get into. Line sectionalizer. You know, it's a device that automatically isolates faulted sections on the line from a distribution system. It may not have the fault interrupting capability of maybe a recloser, but they're usually fairly smart and programmable, and you can build in some automation to them. Similar to a recloser, you can build in a lot of automation to a recloser. So, I already talked through a decent amount of that. Right, it's a switch designed to disconnect power devices at no load conditions. That's a disconnect switch. You got your load break switch. Right, we talked about it's designed to interrupt load currents, but not larger fault currents. And then you got your circuit breakers. I guess a circuit breaker is technically a switch. It's a more complex switch, definitely. But you know, that's designed to interrupt larger fault currents. Switches are also used quite a lot for isolation. You know, the example that we talked about here, right? You open that switch, you open that switch. Now this portion of the distribution circuit is, you know, safe to work on. So they're cheaper than breakers, right? You know, a breaker would be expensive. You wouldn't, you know, probably able to afford breakers in all of these situations, but you can use the switches, you know, for isolation if you want to safely work in an area. The fuses, they're designed to blow within a specified time for a given fault current. Andrew may have put some of them up on time current curves in Aspen for you, which if he didn't, well, you know, we'll get into more. But they do have a time current characteristic. So the fuse has got two major components to it. You've got your minimum melting current. That is really a plot of, you know, when are you going to start melting? Now, once a fuse has started that melting process, right, it's damaged permanently, and you know, its rating at that point has been altered, usually to operate faster, you know, from there on out. Then you've got your total clear, and that's a plot of the maximum time versus the current required to melt and fully isolate the fault and, you know, extinguish any harm. Like the pros and cons of fuses, like I said, they generally don't fail because they're simple. The cons of a fuse, you got to go out and replace them once they're blown. That is expensive, right? You know, you got to have a technician go out, find it, you know, bring the right fuse with them, replace it. So that, you know, that technician's time is expensive. And then also restoration times are a lot longer, right? Now, whatever load that fuse is feeding, those people are going to be, you know, without power for, you know, that portion of time. You know, could be a couple hours. And the other maybe downside to fuses is a lot of the times it's not practical to coordinate fuses with ground overcurrent elements at lower fault values. Right, fuses are you know, phase elements by nature, I guess you could put one in the neutral, but that's not common. But it's generally difficult to coordinate them with more sensitive ground over current elements. Yeah, sometimes you got to compromise with an intersection point. So one type of fuse is an expulsion fuse. And the fuse link acts as a weak link that can melt due to the heat associated with the overload or fault. Yep, I talked about that. They use various materials and dimensions. That really is used to define that current characteristic. I think that's fairly intuitive, right? Maybe you've got a fuse link with a material that has a higher melting point. Right? It's going to take more current. So I think that's fairly intuitive. The fuse links are contained in a tube with a deionized lining. We'll get into why that is important. Right, if you visualize a fuse, I'm sure most of us have, right, we know that then we can visualize that tube. And then, like I said, it's lined with a material. So for an expulsion fuse, when the fuse link melts, like any time you're interrupting high currents, an arc is generally created, which breaks down that lining and emits deionizing gases that help extinguish the arc. So the important part about extinguishing that arc, right? You want to get rid of that oxygen, essentially, right? That's allowing the arc to go across two areas. Right, you get rid of the oxygen and get rid of the arc. That's the goal there. Current's usually fully interrupted at a natural zero crossing. And then if you guys have never seen it, I guess it's interesting to see where we get the term expulsion. High pressure gases are then expelled from both ends of the tube. You can see that there. So we talked about those characteristics for a fuse. This is a plot from Aspen one-liner, what you guys had worked with. This is an example of a 34.5 kV fuse, line-to-line rating. It's got a 200 amp rating. It's characterized as a slow speed fuse. And then, in Aspen, all fuses usually have a time curve number that's just associated with it. So we can see the two characteristics, kind of the top portion of this right there. That's going to be the total clear. And then that portion there is that minimum melt. Shaded area is the difference. And we can see these things operate pretty fast for higher fault currents. That's in seconds. What is a cycle? Is it 0.167? You can definitely get down, below a cycle there. Same one. Yeah, here's a fuse kind of shown from a manufacturer. I think it's the same fuse we had here, right? Yep. So this is their data sheet. This is how they would show it. It looks like they have different sizes all shown in the same data sheet. You've got that 200 amp fuse all the way down to 15. The shape pretty much stays the same. It's just that rating that moves. It looks like this fuse in particular, gives you this data as a PDF. It looks like it actually gives it to you in Excel also. So this is a situation where maybe if you can't afford Aspen, because I think Aspen's like $7,000 a year for a license. If you can't afford that, you might be able to build this in Excel and do some coordination at a much more cost-effective. A different type of fuse, our current limiting fuse. They're not expulsion fuses, but one thing about them is they limit the available fault current through the fuse. For a current limiting fuse, the tube is filled with sand. And this arc causes the sand to melt into glass. So this restricts the arc by increasing the resistance and reducing the current to zero. It almost, we'll say, pinches off the fault current. It's going to be a lot faster than an expulsion fuse. It can do this act before that first zero crossing, and by doing that, it truly limits the current. Right, it never gets up to a value, a full fault value that we might see the different type of fuse. Like a regular fuse, they still have that time current curve characteristics, but they also have a let through characteristic. Got an example of this here. The way that this ends up working, and maybe I should give a paint. So when I say current limiting fuse, what'll end up happening is, let's say you've got a breaker, a typical fuse here. So let's say this was just a normal expulsion type fuse. If a fault were to happen here, you might have 10,000 amps of available fault current. What a current limiting fuse can actually do is pinch that thing off before it gets to its full, its full peak value, if you would. That's how fast it is. It'll pinch it off before it gets to that full peak value. And in that case, it may actually limit it. If this is a current limiting fuse, maybe what may have normally been 10,000 amps, right, within your system, it can pinch it off and reduce that current to maybe, let's say, 5,000 amps. And the way that you can tell how much that happens is with this current let through curve. Let's say this particular system, if there wasn't a current limiting fuse and that fault were to happen, let's say there would be 6,000 amps available. Right, you can get that number from a short circuit study from a program like Aspen. So let's say it had 6,000 amps available. So the way that you would figure out how much it's going to get pinched off to is you can come in here and you go up to your fuse of interest. It looks like this top line is for a 25 amp fuse or a 20 amp fuse. You get to that line, you draw over to this other diagonal, and then from there, you really got two options on what you want to do. In this situation, we draw a line back down, and that tells us we've got about 2,100 amps available. Now, this is an RMS value. By RMS, I mean the root mean squared of that sine wave. If you want to, you can also look at this as a peak value. I have it as RMS here because that's usually what I'm interested in. I'm a relay guy. Relays filter out, a lot of offset, things like that. And, they operate off of RMS. But if you want to, you can look at this whole thing in terms of peak current, which would be, the top, of that curve. So if you were to draw this line to the left rather than draw it down, it'll give you that peak current, which I have here as 2 times the square root of 2 of the RMS. I think that comes out to what, 2.818. The reason it's 2 times square root of 2 is you got your DC offset, as we talked about, right? You got your RMS. Your peak is going to be 1.414 times your RMS, and then you got your DC offset, which at a max is always going to be 2 times peak. That's the worst case scenario. All right, and then you've got your sine wave riding on top of that, essentially. So that point right there is really what this left side of the curve represents. Like I said, I'm more interested in the RMS. I would say if you're ever doing any coordination with a current let through curve, this is what you're going to be doing, right? You start at the available fault current, you go up to the line, you go to the diagonal, you go back down. All right, similarly, if we had a, maybe a 10 amp fuse, right, we would come to here and, draw it like that. So. All right, so coordinating with fuses, which you would, do in a program like Aspen. Let's see where we're at. Okay, we're doing good on time. Coordinating with fuses. So, and this is from a relaying perspective. A typical curve that you might see to coordinate with a fuse might be a U4. That's a Schweitzer specific curve, which is classified as extremely inverse, and that often best fits the shape of that curve of that fuse. It's their shape that best fits this. It hugs that well. Now they call it extremely inverse because you can almost think of that as extremely vertical. So you would have an EI curve, right? An extremely inverse curve. But in contrast, something that looks like that might be a very inverse. Right, it's not quite as vertical. Then, they've got, an MI, a moderately inverse, and then, maybe something like that is just inverse. If you want to visualize those terms, that's kind of how they're laid out. It says inverse. I almost view that word as vertical. Extremely inverse being the most vertical and the one that I think best fits these fuses. Once you do a lot of relay coordination, a lot of times you'll be like, oh, there's fuses out there. Boom, U4. You'll get that with experience. So when coordinating with a fuse and coordinating anything in general, and by coordinating, I guess what I mean is what I talked about, if a fault were to happen right here. When I say coordinating, I mean making sure that that fuse operates faster than that breaker and making sure that everybody else stays online. That's what I mean by coordinating. So when coordinating, the fuses are coordinating really in general. Different customers or different utilities, they may have different requirements as far as what they want to see for coordinating time intervals. A coordinating time interval being the time between two devices that are operating. Let's say that breaker that I was talking about would operate in a half second, and the fuse were to operate in a quarter second. That coordinating time interval would be a quarter second. So different places have different requirements. A pretty typical one that I have here for fuse coordination, I think it comes from the IEEE. They want to keep that time difference, or they recommend keeping that time difference at either 0.12 seconds of difference, or a relay operate time that is at least 130% of a fuse total clear time for that maximum fault current, whichever is greater. So by that, what I mean is, let's say we have a fault here at 2000 amps. And that total clear time is going to be 0.7 seconds. When I say I want the relay to be 130% faster, basically what I'm saying is I want that relay to operate in 0.7 times 1.3. Here. 0.7 times 1.3, 0.91. In order to have the margin that we want, it would have to operate in 0.91 seconds or slower, which it looks like it does here, right? That's about maybe a second and a quarter. So that'd be the goal that we're explaining there. And then I think I mentioned earlier that ground relaying is often set more sensitively than fuses would allow. Right, a fuse must be set above load, where a 51G element that really only operates on that imbalance that we want to be sensitive, that may be set less than load. So in that situation, what might happen is you may pick an acceptable intersection point, and you might pick something that allows that fuse to have ample time to blow, but that can still allow the relay to detect those sensitive situations. An example of that might be maybe a high impedance ground fault where it's not creating a lot of fault current, but luckily, that ground element was sensitive and can detect it. So that intersection of 20 seconds that I'm talking about there, a way that you may see that is maybe your ground overcurrent element. Oh, geez, I'm a terrible artist. That ground overcurrent element intersects the fuse, at a time, in that example, greater than 20 seconds. So that's kind of a compromise, if I would. That's a situation maybe your relaying is an art rather than a perfect science. So yeah. So some other considerations for coordinating with fuses is derating for reclosing. Basically, we haven't gotten into the reclosing stuff yet. but it's relative for fuses, I guess. So I think we talked in that first class that most faults are temporary by nature. With that, a lot of times we'll do something called reclosing, where let's say you had a temporary fault, and maybe squirrel touches the line, right? You trip, squirrel burns, falls to the ground, breaker recloses, squirrel's gone, you're happy. So that, that's why we have reclosing. Now, how that relates to fuses is, let's say it's not a squirrel that burns off. Let's say it's a permanent fault. You still want that fuse to clear faster or slower than a recloser. The challenging part with that is this fuse is going to be warm. Right? Let's say relay trips and then is open for 5 seconds and then recloses. If it has to, detect that fault again, then that fuse would already be hot going into that next, fault detection, and it's going to operate quicker because it's already hot. So in that situation, there's actually a method to derate the fuse to try and coordinate that situation. This maybe is a less common thing that you run into. This all revolves around the fuse actually being upstream, which may be a little bit less common. Right, fuse is upstream, and then maybe you've got a recloser downstream. Fault happens here. You want recloser to go first, fuse to go second, but fuse is hot. It's going to go faster. It's going to make that more difficult. So in this situation, we've got some factors that can be multiplied to your curve to really adjust that fuse. So it's got two multipliers, one being if you have one fast curve that you're trying to coordinate with, and then two if you've got two fast curves that you're trying to coordinate with. Sometimes those recloses will actually have multiple shots. It's not just, one trip reclose. They may trip, reclose, trip, reclose. And that just makes that fuse get a little bit hotter. So you can see those numbers are a little bit higher. And then here are the reclosing times kind of associated with those numbers. So let's say that open interval, which we'll get into that, the time essentially that you allow that squirrel to fall to the ground. The shorter you have for a reclosing interval, right, the more you gotta derate it. The longer you give it more time to cool down, the less that you would derate it. So I know I keep going back here. That K factor essentially would, move this guy up and down and reduce that coordinating time interval. Let's see. Oh, it's 6. Do I want to get to reclosers? Yeah, I'll get into reclosers real quick. So I apologize. This was maybe a tough thing to organize. We started with fuses. They're the most simple devices. End up talking about reclosers because they're relevant to fuses without actually getting into the recloser portion of the presentation. So I apologize for that. Yeah, I guess at this point, does anyone have any questions?
Yeah, I got a question, I guess.
Yeah.
I'm just curious, like, what the fuses look like. Like, how big would they be on the lines or anything like that? Is there one in this picture?
Nope, that's a recloser. But you know who knows the answer to this? Google.
Oh yeah.
Yeah, here's a good example. So that's a good
cool.
example. Yeah, that's a good example of I think that's a 34 kV fuse. Oh, I'm gonna close the door. I can hear my kids in the background. Yeah, so here's a fuse in this situation. A lot of the times what will actually happen also um, is after one of these things operates, it'll actually swing down. It kind of gives you a visual of that. Um, so looking at this whole thing, right, you've got your fuse. You can see that's where, you know, it connects in. It sounds crazy, but it's a normal operating situation. Sometimes what technicians will do is they'll have a long fiberglass pole and they'll actually grab that little loop and they'll open it manually and almost use it as a disconnect. You can see that one's actually got a little bit of a bigger ring to grab onto. But then right here, you can see, right, that's where you would bolt into your conductors. You would have a similar place to bolt down here. You've got your insulators right here. And then, right, that's where you would bolt onto a structure. So, yeah, these are some pretty common fuses you might see. You know, it looks like they all have different mounting, you know, different ways for mounting. But yeah, I guess maybe I'd say about the size of your forearm.
Oh, cool. Yeah, definitely looks different than I thought it would. But yeah, thanks, Leo.
Yeah, of course. And then yeah, trying to play with time a little bit here. Looks like we got about 10 minutes left. I don't want to dive deep into reclosers with knowing that we're gonna just get started. I guess kind of on that visual here, we can start identifying some of the stuff here. So this is a pretty modern recloser. It's up on the top here. You can actually see this guy right here. That is a voltage transformer. It can be used for two things. It can either bring power to your recloser controller, which you would see down at the bottom of the pole, and we'll get into here in a couple slides. Or it can be used to, you know, be voltage sensing for your voltage for your recloser controller. Right? You can have over voltage elements, under voltage, you know, be used for directionality, things like that. So that's your voltage transformer. Right in here is actually where you're going to have your interrupters. Then you've got some bushings in here, CT bushings as well. So you can see, right, power comes in from one side, comes down here, boom, comes in the top. You're going to have your bushings for your CTs, right? That's where it's going to sense the current. It's going to send that current to your recloser controller, and it's going to make decisions, you know, based on that current for overcurrents. Right, and then you can see it comes down here. Right in the middle here, you're going to have an interrupter. This is where the recloser actually opens and isolates that fault current. And then comes out. And okay, right, we're going to continue on our way. Yeah, I guess a pretty common, you know, arrangement there. Similar to the fuse, you can see these little yellow handles right here. You know, you can grab onto those and that'll actually open this up as well as an option. So, and then what are these up here? Are these actually fuses up here? You can't really tell. Are they just disconnects? Those looks like they may just be disconnects. But yeah, I guess I don't want to dive into the reclosers too deep without with us getting immediately cut off. I guess off the top of anyone's head, do we have any questions about this? No. Alrighty. I guess I did want to take maybe a couple minutes before we finish up. So I know last time we got together, we had a session where we went down to the lab and connected to the relay and did some some basic things with the relay like pushing settings, pulling settings, connecting to the relay, looking at the SER, that kind of stuff. I was hoping on Tuesday, which would be Tuesday the 11th. This Tuesday coming up, Tuesday the 11th at 5. We could do a similar thing. We could go down to the lab and do some stuff with the relays. Basically, what I had prepared a while back was a logic diagram for those relays in the lab. And really what the goal is going to be here is, we'll take one of these logic diagrams and we're actually going to, test the logic is the game plan. So, we come through here, we'll push the push button, we'll see, the light turn on, see the light turn off, right? It says that this is going to go to the trip equation. Okay, we'll follow that out and, see what it does. We'll operate the switches. We'll put it in different modes. The goal will be to actually see this, this logic, operate in the relay. So, because I know I talk a lot of numbers in the lecture. That's maybe not the best for everyone. So, yeah, it'd be really great to meet in person Tuesday at the lab. Run through this. Normally, I like to do this the last part of the 3 lecture series for distribution because you get to see more of the lecture. I'm going to be honest, Jude's on campus Tuesday, so I'm picking Tuesday. She's not on campus Thursday, so I'm not picking Thursday. But it'd be great to see as many of you guys as possible. And I think it's worthwhile if you live in the area. I know some people are remote to actually be able to see the relay operate. So yeah, figured I'd let you guys know about that. And we'll do that Tuesday, and then Thursday we'll pick back up on reclosers. So
do we have any homework for in this lesson?
Oh, I'm sorry, I didn't hear you there.
I mean, do we have any homework?
Yes, yep, you do have homework. I don't know if Paul uploaded that or not yet.
Was it the SCADA one?
No.
It's not up yet. They just put up a one-liner one and the exam. It looks like midterm.
Yeah, this is the one that I'll put up. I don't think it's been uploaded yet. Let me write that down because if I don't send that to Paul, he won't know to upload it. But yes, there will be distribution homework.
Thank you.
Okay. And then with homework, as a word of caution, it's fairly easy to spot AI these days. So keep an eye out for that. Yeah, it doesn't do as good of a job as you might think it does. So yeah, keep an eye out for that. Sometimes I honestly think it's easier just to look in the book or lecture than what trying to deal with trying to figure out if AI is giving you the right information or not. So yeah, I guess with that, I'll let you guys go, and we'll catch up Thursday.
Hey Leo, I just got a quick question about like which day you wanted to go into the lab again?
Yeah, it'll be Tuesday, this Tuesday coming up, the 11th, March 11th.
So
No,
it's the 13th, isn't it?
18th. Today's the
Oh
16th.
shit! Wow, I was looking at the wrong part of my calendar. The 18th.
Yes.
I am very
Oh, but
glad you pointed
also-
that out.
I think we're on spring break next week too. So
Are you?
Yeah. Spring
Yeah.
break starts Monday.
Wow, I am totally off of my calendar. Okay. So that would then be the 25th.
okay. Sounds good.
Let me put that in my chat. Lab March 25th for relay testing. Thank you for pointing that out. When I was looking at my calendar, I was looking at the current week, right? So that's why I got the 11th. Didn't realize next week was spring break. So yeah, 25th. Sorry about that, guys.
It's all right. Yeah, sounds good. I'll be able to make it to that one, so I'll see you then.
Yeah.
Mhm.
Yeah, and if you can't make it, it'll be like last time. You know, we'll be doing our best to have a live feed on it. So hopefully there's not too much lag. I know last time there was a little bit of lag. I guess the Wi-Fi in the basement's not perfect. So yeah, looking forward to it, guys.
Awesome.
Thank you.
I just wanted to add, I was looking, I guess, to the class. I was looking at the midterm, and when you open it up on the PDF, it has a due date of the 21st. But I saw on Canvas or Black Brightspace, you know, it's marked as the 25th. So I guess be careful of that. There's a chance it's due on the 21st.
Okay.
Were you gonna send Paul a reminder? Or would you? I don't mind shooting him an email
Um,
and saying, "Hey, what's up? What's the right date?"
Yeah, I wasn't planning on it. If you want to,
Yeah, I
probably
don't mind
just-
doing that. I'll send him an email
Yeah.
and ask him to post it to Brightspace what day he actually wants it. So
Awesome. Appreciate it.
All right. Well, sounds good, guys. I appreciate the time, and I appreciate the questions too. They're all great. So it's awesome. Yeah,
thanks, Leo.
yeah, talk to you later.
Yeah, thanks, Leo. Have a good one.
Thanks.
Thank you. Thank you. Have a good day.
Acid down controversy.
And it, it is a Kansas, so it really has more to do with how far we can transmit that power. If you're going to transmit it 100 miles, right, we have a high voltage to reduce losses. If we only have to go maybe a mile, it's a short run from that distribution station to, the loads, and maybe we got lower and lower kV. So, the primary, we go down to primary distribution. That's the voltage range we're really talking about today, that 4 kV to 35 kV.